A world with no sunrise. Would you live there? Could you live on a world with no sunrise? A planet where the star never moves in the sky, where one hemisphere bakes in endless daylight, while the other is locked in permanent night, where morning and evening are not times of day, but places on the map. Imagine standing there. Above you, a red dwarf star hangs in exactly the same spot, forever frozen in the sky. Shadows never change direction. The landscape around you is locked into a single eternal hour. If you walk toward the light, it only gets brighter. If you walk toward the darkness, the star sinks lower, until it fades into a sky of unbroken black. Could you ever truly call that place home? We talk about habitable planets all the time. In the hunt for alien life, habitable usually means one thing: liquid water can exist on the surface. The right distance from the star, inside the so-called Goldilocks zone, with temperatures that are not too hot and not too cold. But while that definition works well for our telescopes and our data, it leaves out something crucial: what it would actually feel like to live there. Is a planet really habitable if its sky never changes? If half the world is a scorched desert and the other half a frozen nightside, does habitability only describe chemistry and climate? Or does it also include psychology, culture, and the rhythms of life that shape our days and years? This means that when we call a world Earth-like, we may be saying far less than we think. So, let's begin with a real example. TOI-700d, a small, almost Earth-sized planet orbiting a cool red dwarf star about 100 light-years away in the constellation Dorado. Discovered by NASA's TESS mission, it sits comfortably in its star's habitable zone and completes an orbit in just 37 days. Climate models suggest it is probably tidally locked, showing the same face to its star at all times. No sunrise, no sunset, just an eternal dayside and an eternal night. It should be noted that this makes TOI-700d one of the most intriguing nearby test cases we have. If life can adapt to a world this alien, with a permanent day hemisphere, a frozen night side, and a narrow twilight band between them, then our ideas about where life can exist in the universe suddenly expand. Optimistically speaking, worlds we once dismissed as too strange might turn out to be thriving. But if TOI-700d fails that test, if even a nearly Earth-sized planet in the Goldilocks zone cannot sustain a stable atmosphere or friendly climate under these conditions, then our search for true Earth analogs becomes narrower and more focused. So it's time to find out the truth. By the end of this video, we will build a concrete, sensory picture of what a day, a year, and even a lifetime might feel like on TOI-700d, based on the best current models of its atmosphere, its climate, and its strange, unmoving sky. Why this one planet could rewrite the rules of habitability. But why does this one distant world matter so much? And what happens to our place in the universe if TOI-700d turns out to be truly habitable? In the hunt for alien life, we often talk about Earth-like planets around sun-like stars. It feels comforting, familiar. But while that picture is intuitive, it is also misleading, because most stars in our galaxy are not like the sun at all. They are small, cool, red dwarfs. This means that if their planets can host life, the Milky Way might be overflowing with habitable real estate. If they cannot, then truly friendly planets like Earth may be astonishingly rare. Red dwarfs dominate our stellar neighborhood. Proxima Centauri is one. So are the majority of the closest 60 stars to us. They sip their fuel so slowly that they can shine for trillions of years, far longer than the sun. On paper, that sounds perfect for life. A long-lived, steady energy source, and a tight Goldilocks zone where a planet can orbit close in and stay warm for eons. But while their lifetimes are generous, their tempers are not. Many red dwarfs blast their planets with powerful flares and streams of charged particles. It should be noted that for a world huddled very close to such a star, those outbursts can strip away an atmosphere, sterilize a surface, and turn a promising ocean world into bare rock. So when we ask whether red dwarf systems are truly habitable, we are really asking whether their planets can survive this violence long enough for biology to take hold. And here is the scientific challenge. We cannot visit these planets. We can barely see them at all. Instead, we infer their existence from tiny dips in starlight as a planet crosses the star's face, and from subtle gravitational tugs that slightly shift the star's motion. From those fragile pieces of data, we try to reconstruct size, mass, orbit, and even hints of an atmosphere. Every conclusion is provisional, and every improvement is hard-won. So let's begin to see why TOI-700 is different. This system, about 100 light-years away, hosts several planets, but TOI-700d stands out as an almost perfect test case. It is very close to Earth-sized. It orbits in the Goldilocks zone of a relatively quiet red dwarf, and its 37-day year almost certainly means it is tidally locked. Optimistically speaking, that combination makes it one of the best nearby laboratories for asking whether a small red star can host a truly life-friendly world. TOI-700d sits right at the intersection of hope and skepticism. On paper, it looks nearly ideal, yet a single missing ingredient or a single unseen catastrophe in its past could make it utterly barren. So what does the evidence actually say about this planet's atmosphere, its climate, and its chances for life? And what happens if the truth is not what we expect? Meet TOI-700d, our quiet, nearby test case for alien life. So to even start answering those questions, we need to meet the world at the center of this mystery. TOI-700d does not live in isolation. It circles a small, cool, red dwarf star called TOI-700, about 100 light-years away in the southern constellation Dorado. That is close in cosmic terms. Close enough that our telescopes can collect detailed data on the system's light, and maybe, one day, on the fingerprints of a living atmosphere. Red dwarf stars are the workhorses of the Milky Way. They are smaller and dimmer than the sun, but they burn their fuel extremely slowly. This means their habitable, or Goldilocks zone, huddles very close to the star. TOI-700 is no exception. It should be noted that this particular red dwarf appears relatively quiet, with fewer violent flares than many of its cousins. In the hunt for alien life, that calmness is not just a detail. It is a lifeline for any fragile atmosphere clinging to a nearby planet. Into that gentle glow falls TOI-700d. On paper, it looks almost disarmingly Earth-like. Its radius is about 1.1 times that of Earth, placing it firmly in the rocky, terrestrial category. It completes one tight orbit in roughly 37 days, close enough that it receives nearly the same amount of stellar energy our planet gets from the sun. If you only saw those numbers, you might be tempted to call it a second Earth and move on. But while the energy budget looks familiar, the experience of standing there would be utterly alien. At such a close orbit around a low-mass star, gravity and tides almost certainly have locked TOI-700d so that one hemisphere always faces the star. One side in endless day, one side in endless night. A thin ring of permanent twilight in between. So let's begin to imagine. Where would oceans form? Where would clouds gather? Where would life, if it exists, choose to make a home? Part of what makes this system so intriguing is that TOI-700 does not host just one planet. We know of at least 4, B, C, D, and the later discovered E, all packed into a compact, clockwork-like arrangement. Yet only TOI-700d sits squarely in the Goldilocks zone, where surface liquid water is most plausible. The others help us understand the system's history, but D is the main stage for habitability. Optimistically speaking, TOI-700d is one of the most promising nearby Earth-sized habitable zone planets we have. The star's relative quietness and climate models both hint that stable, life-supporting conditions are possible. This means the right atmosphere could transform that tidally locked world into a temperate ocean planet with mild conditions under a fixed, unsetting star. Or not. With a thick blanket of greenhouse gases, it could resemble a Venus-like hothouse. With only a thin veil of air, it might be a harsh desert, its water trapped as ice on the dark side. So it's time to find out the truth. In the next sections, we will explore how different atmospheres could radically reshape TOI-700d and decide whether any of them could truly host life. From TESS to telescopes of tomorrow, how we'll probe TOI-700d. If we want to decide which version of TOI-700d is real, we need more than imagination. We need instruments that can turn this distant point of light into hard evidence. In the hunt for alien life, that story starts with a surveyor, NASA's TESS mission. TESS does not zoom in on one planet at a time. Instead, it stares at huge tiles of the sky, measuring the brightness of hundreds of thousands of stars at once, including quiet little red dwarfs like TOI-700. It watches patiently for tiny, rhythmic dips in starlight. What are those dips? Think of TESS as a cosmic heartbeat monitor. The star's brightness traces a nearly flat line, pulsing steadily. Then, every 37 days or so, the line drops by a fraction of a percent and comes back up. Each repeating dip is the shadow of a planet crossing the star, a transit written directly into the light curve. This means that just from those dimmings, we can already read out some basic facts. How deep the dip is tells us the size of the planet compared to the star. How often it repeats gives us the orbital period, and, using the star's mass, the distance of the orbit. That is how TESS flagged TOI-700d as an Earth-sized world in the Goldilocks zone of its system. But while this transit method is powerful, it is also frustrating. It reveals the clockwork of the orbit, not yet the face of the planet. We do not see oceans or continents. We do not see whether an atmosphere is there, let alone if it is breathable. So it should be noted that TESS is just the first step, the scout. To move from silhouettes to chemistry, we need a different class of telescope. Enter the James Webb Space Telescope and the observatories that will follow it. Instead of only measuring brightness, Webb can split the starlight into a spectrum, like stretching a rainbow into thousands of finely spaced colors. When TOI-700d transits, a thin ring of the star's light filters through any atmosphere the planet might have. Certain gases absorb certain colors. Water vapor, CO2, methane, oxygen. Each leaves its own fingerprint. Here is the pattern interrupt. For TOI-700d, these telescopes are not just cameras. They are verdict machines. Over years of careful observations, they can tell us whether this world is wrapped in a choking greenhouse, buried under reflective clouds, or cloaked in a mild, potentially habitable sky not unlike Earth's. Optimistically speaking, TOI-700d is close and calm enough that future instruments beyond JWST could even map temperature patterns between its day and night sides. But we are not there yet. We do not have Webb-quality spectra for this planet today. What we do have are precise TESS orbits, stellar properties, and sophisticated climate models. So let's begin to use those tools to predict what we should see when those first precious photons finally arrive, and which atmospheric scenarios will keep TOI-700d in the race for life. Paradise or pressure cooker? the two faces of TOI-700d. Those tools leave us with a surprisingly stark question. Is TOI-700d a gentle twilight world where oceans breathe under a soft sky, or a suffocating pressure cooker more like Venus than Earth? In the hunt for alien life, that's the fork in the road that really matters. One picture is almost idyllic. Imagine a planet only slightly larger than Earth, tidally locked to a calm red dwarf, its Goldilocks zone orbit completed every 37 days. The day side is warm but not scorching, wrapped in a modest atmosphere with clouds and maybe even scattered seas. Around the line between day and night, the so-called terminator, you could walk under a permanent sunset, with temperatures hovering near Earth-like values and winds endlessly shuttling heat into the frozen dark. But there is another picture. What if the same stellar energy that could support mild climates instead drove the planet past a tipping point? A little extra CO2, a bit more water vapor, and the greenhouse effect can run away. This means the surface could be buried under a crushing, Venus-style atmosphere, hundreds of times thicker than Earth's, with temperatures hot enough to melt lead solder and clouds made of sulfuric acid rather than water. From orbit, that planet might still look roughly Earth-sized and neatly placed in the habitable zone, yet its surface would be utterly hostile to any life we know. It should be noted that both of these extremes are physically plausible from the data we currently have. TOI-700d receives a similar amount of energy from its star as Earth does from the Sun. Optimistically speaking, that could allow liquid water to exist over large regions, especially if there are oceans to move heat around the planet. But while the orbit and size look promising, we do not yet know how thick its atmosphere is, what it is made of, or whether it ever suffered a runaway greenhouse early in its history. So the real question is not simply, is TOI-700d in the habitable zone? Instead, we have to ask, is it actually habitable in practice? And habitable for what kinds of life, under what conditions, and in which parts of the planet? Could hardy microbes cling to the cool edge of the terminator while the substellar point bakes? Or are we dealing with a world where even extremophiles would be instantly destroyed at the surface? By resolving this tension, even partially, we learn something profound about the universe. Are Earth-like planets around red dwarfs rare gems that manage to avoid the fate of Venus? Or are most of them deceptive dead ends, habitable on paper, sterile in reality? So it's time to find out the truth. In the next sections, we will dive into the physics, run through climate models, and even imagine a day in the life on TOI-700d, if, that is, any life could survive there at all. Who's talking to you, and where we're going tonight? So if we are going to judge TOI-700d fairly, who is actually guiding you through this new world tonight, and where are we taking you? And this is, where we follow the data through the most promising planetary systems in the hunt for alien life. If you've been with us for TRAPPIST-1, Proxima Centauri, and beyond, welcome back. If you clicked because TOI-700d sounded like an Earth-like escape just 100 light-years away, you're in exactly the right place. Our goal is simple to say, but harder to achieve. By the end of this episode, you should be able to answer two questions for yourself. First, would you actually want to live on TOI-700d? Second, do you think any life, from hardy microbes to complex ecosystems, could plausibly survive there? This means we need more than poetic speculation. We need a roadmap. So let's begin with the foundation of everything, the star and its architecture. We will start by stepping back and looking at the TOI-700 system as a whole, a relatively quiet red dwarf in Dorado, its distance from us, and how TESS first revealed its family of planets. Why does this particular star look more welcoming than the more turbulent TRAPPIST-1? And what does that tell us about the chances that atmospheres can endure here at all? From there, we will zoom in on TOI-700d's orbit and physics. How big is this planet? How much energy does it receive? And how likely is it to be tidally locked, with one face in endless day and the other in perpetual night? We will build up, step by step, from gravity and rotation to heat transport, because it should be noted that every detail of that orbit shapes whether TOI-700d sits comfortably in the Goldilocks zone or only brushes its edge. Then we will layer on possible climates and atmospheres. We will test Earth-like air, Venus-like greenhouse shrouds, thin Mars-style envelopes, and deep global oceans. In each case, we will ask, where could liquid water actually exist? Could clouds form a reflective shield? Or would the planet lock into an ice house or steam world? Not as hand-wavy guesses, but using climate models and analogs from our own solar system. Quick pause. Imagine you are not just watching this, you are moving in. For the rest of the video, each section will be another room in your new home on TOI-700d. The unblinking sky above the substellar point, the stormy twilight ring along the terminator, the frozen far side that almost never sees the star. We will finish by looking ahead to JWST and future telescopes, asking what signatures of atmospheres, oceans, and even biology we might realistically measure. Optimistically speaking, by the end, TOI-700d will not just be a name in a catalog, but a place you feel you've visited, long enough to decide whether you would stay. The rules of alien real estate. What makes a world livable? Before we can decide whether we would stay on TOI-700d, we have to ask a deceptively simple question. What does it actually mean for a world to be habitable? We talk about the Goldilocks zone as if it were a neat ring around a star, but in reality, it is more like a shifting, fuzzy band shaped by physics, chemistry, and even biology. In the hunt for alien life, habitable usually means one thing above all: the long-term presence of liquid water on a planet's surface. But while that sounds straightforward, the path from starlight to stable oceans is anything but. Stellar brightness, the color of the light, high-energy radiation, the thickness and composition of the atmosphere, the planet's rotation, magnetic field, even plate tectonics and microbial feedbacks all push the climate in different directions. This means two planets at the same distance from the same star can end up as an ice ball and a steam bath. So let's begin by separating the rules of alien real estate into two pieces: the star and the planet. The star sets the energy budget. Its luminosity tells us how much power is available. Its spectrum tells us what kind of photons are arriving. Its flares and winds define the radiation environment that can strip or sculpt atmospheres. It should be noted that the star's lifetime also matters. A world may pass briefly through a comfortable zone, but if the star evolves too fast, there is no time for complex life to adapt. The planet, on the other hand, decides what to do with that incoming energy. Its atmosphere absorbs, reflects, and redistributes heat. Clouds can cool or warm. Greenhouse gases like carbon dioxide and water vapor can trap infrared light and extend the habitable zone outward. Surface oceans store heat and move it around. Continents and ice caps change how much light is reflected back to space. Even the length of the day and the tilt of the axis control weather patterns and climate cycles. For a tidally locked planet like TOI-700d is likely to be, rotation and orbital dynamics move from background details to center stage. One hemisphere faces the red dwarf in eternal day, the other lies in permanent night. Will thick air and strong winds carry enough heat to keep the dark side above the freezing point? Or will water, if it exists, be trapped as ice there? Could a narrow ring along the terminator, where star and darkness balance, host rivers, clouds, maybe even an Earth-like climate band? Optimistically speaking, climate models say it is possible. So it's time to find out the truth about the specific landlord in this cosmic deal. Before we can imagine seas and skies on TOI-700d, we need to understand the red dwarf it orbits, how bright it is, how violently it flares, and how stable it has been over billions of years. A quiet, long-lived star can nurture atmospheres. A wild one can strip them bare. In the next section, we will step back and meet TOI-700 itself, and see why this particular red dwarf is both promising and problematic for life. Inside a red dwarf's glow, TOI-700's stellar personality. So let's begin with the star at the heart of this story. If TOI-700d is our potential oasis, then TOI-700 itself is the strange red campfire trying to keep it warm. TOI-700 is an M-dwarf, a red dwarf star about 100 light-years away in Dorado. Compared to our Sun, it's smaller, cooler, and dimmer, glowing with a soft reddish light instead of harsh white. This means its luminosity is far lower, so its habitable, or Goldilocks zone, is tucked in incredibly close. TOI-700d orbits at a distance where a year lasts only about 37 days, yet it still receives roughly Earth-like energy. Red dwarf stars like this dominate our galaxy. It should be noted that when we look around the local neighborhood of the Milky Way, most of what we see are not sun-like stars at all. They are tiny, cool, red dwarfs. They vastly outnumber stars like the Sun, perhaps by a factor of 10 or more. And because they sip their fuel so slowly, they can burn for hundreds of billions, even trillions of years. In the hunt for alien life, that kind of timescale is intoxicating. It offers unimaginably long windows for biology to start, crash, and restart again. But while their longevity is a gift, their temperament is often a curse. Many red dwarfs are magnetically active, unleashing powerful flares, intense stellar winds, and bursts of high-energy radiation. For planets huddled close to stay warm, that proximity can be brutal. Over millions of years, those winds can strip away an atmosphere, molecule by molecule, turning a once habitable world into bare rock. This means that for most red dwarf systems, the Goldilocks zone can look less like a safe harbor and more like a firing range. Now connect that close-in orbit to another consequence, tidal locking. When a planet orbits so near its star, gravity acts like a cosmic brake, slowing its spin until one hemisphere always faces the light. For TOI-700d, most models suggest exactly this. One side in eternal day, the other in endless night, with a narrow ring of twilight between. Whether an atmosphere can survive, circulate heat, and stay habitable under such extremes is one of the central questions for this system. Optimistically speaking, TOI-700 seems quieter than many of its red dwarf cousins, with fewer violent flares in the data we've gathered so far. So it's time to find out the truth. Is this a rare example where a red dwarf's Goldilocks zone is truly welcoming? Or is TOI-700d still living on the edge of a danger zone? In the next section, we will step onto that tidally locked world and ask what day, night, and climate would actually feel like there. A surprisingly calm red dwarf, why TOI-700 gives us hope. To answer that, we have to step back from the planet for a moment and look closely at the star itself. Because if TOI-700 is truly calmer than most red dwarfs, everything about life on TOI-700d changes. Red dwarfs have a reputation. They are small, cool, and incredibly long-lived. But they are also infamous for violent flares that can strip atmospheres and bathe nearby planets in intense radiation. Proxima Centauri, for example, regularly erupts with blasts hundreds of times more energetic than typical solar flares. TRAPPIST-1, while relatively quiet for its class, still shows frequent bursts in the data. But while those systems behave like cosmic strobe lights, TOI-700 appears more like a steady lantern. So what do we actually see? From TESS and follow-up observations, astronomers have monitored TOI-700's brightness over long stretches of time. They do not see the constant, towering flares that plague many M dwarfs. There are variations, yes, but the star's light curve looks subdued, with fewer spikes and less dramatic energy releases. This means, at least in the data we have so far, TOI-700 is a comparatively quiet red dwarf. Why does that matter so much? In the hunt for alien life, the difference between a raging and a relaxed star can be the difference between a planet with a thick, protective atmosphere and a bare, airless rock. High-energy flares blast out X-rays and ultraviolet radiation that can erode the upper atmosphere, especially on planets locked in close orbits. They can shred ozone layers, break apart complex organic molecules, and raise surface radiation to hostile levels. A calmer star gives fragile chemistry a chance to survive. It should be noted that we are still early in the story. We have not watched TOI-700 for billions of years, only for a tiny snapshot of its life. But we can compare. Some red dwarfs flare dozens of times per day, with events hundreds or thousands of times more powerful than anything our sun routinely produces. TOI-700, in contrast, shows far fewer such events in the same observing windows, and the ones we do see look modest. Over geological timescales, that kind of difference adds up. Optimistically speaking, a star that gentle could allow TOI-700d to hold on to a dense atmosphere, perhaps rich in nitrogen, carbon dioxide, and water vapor, for billions of years. With less atmospheric erosion, there is more room for oceans to persist, for clouds to form, for a true Goldilocks zone to exist, instead of just a mathematical line on a chart. So it's time to find out the truth. In a galaxy packed with temperamental red dwarfs, is TOI-700 one of the rare, genuinely welcoming hosts? If it is, then every planet in this system's habitable zone becomes a priority target. And in the next section, we will finally descend to the surface of TOI-700d and imagine what that long-term stellar calm might actually feel like under an alien sky. How we first met TOI-700d, the TESS discovery story. To understand what that calm might feel like on the surface, we first have to ask, how did we even find this quiet little system in the first place? In the hunt for alien life, TOI-700 did not begin as a celebrity. It started as just another faint red dwarf in the southern sky, one of thousands that NASA's TESS spacecraft was quietly watching. TESS, the Transiting Exoplanet Survey Satellite, has a simple but powerful strategy. It stares at one sector of the sky for about a month, measuring the brightness of every star, every 2 minutes, with extreme precision. Then it moves on, tile by tile, building up a map of how stars flicker. Most of those flickers are just noise, but some are not. When a planet crosses in front of its star, the star's light dips by a tiny amount. For an Earth-sized planet, that dip can be less than 1 part in 10,000. This means TESS has to be patient. It waits for the same dip to repeat, again and again, like the ticking of a cosmic clock. In the case of TOI-700, those ticks started to line up into something remarkable. First, the TESS data revealed a short-period inner planet, TOI-700b, whipping around the star in just a few days. Then, a second, TOI-700c, appeared on a wider orbit. But while these inner worlds were interesting, they were too hot to be truly habitable. Astronomers kept sifting the light curve, asking, was there anything farther out in the Goldilocks zone? It should be noted that early on, TOI-700 was even misclassified as a slightly larger, hotter star. That mistake made its planets look bigger and less promising. When follow-up observations from ground-based telescopes refined the star's properties, everything changed. The planets shrank on paper, slipping into the Earth-like category. And then, TOI-700d emerged, a repeating 37-day dip, subtle but persistent, corresponding to a planet about 1.1 times Earth's radius, receiving roughly the same energy from its red dwarf as we do from the Sun. Optimistically speaking, this was exactly the kind of world TESS was built to find. Ground-based teams pointed their telescopes at the star, confirming that these signals were not stellar spots or instrumental glitches, but real planets in orbit. TOI-700d was quickly flagged as a top target for future atmosphere studies, a nearby laboratory for testing what a habitable world around a calm red dwarf might look like. So let's begin to see TOI-700d not as an only child, but as part of a compact family. Later test campaigns, combined with refined analyses, uncovered yet another world, TOI-700e, also Earth-sized, tucked just inside D's orbit. This means TOI-700 hosts at least 4 known planets, with D and E straddling the habitable zone like 2 stepping stones. So it's time to find out the truth. On a world discovered as a tiny dip in starlight, what does that eternal red sun look like from the ground? And could anything be alive beneath it? Reading shadows, how transits reveal an invisible world. So how do we go from a tiny dip in starlight to bold claims about a potentially habitable, Earth-like world? To trust anything we say about TOI-700d, we first have to trust the shadows. When TOI-700d passes in front of its red dwarf star, from our point of view, it performs what astronomers call a transit. The physics is beautifully simple. The planet blocks a small fraction of the star's light, like a moth crossing a flashlight beam. The star briefly looks dimmer. Measure how deep that dip is, and you get the planet's size relative to the star. A 1% dip means the planet's disk covers 1% of the star's surface area. For TOI-700d, the dimming tells us it is just a bit larger than Earth. But while the depth of the dip gives us size, the spacing between dips gives us time. Every time TOI-700d completes an orbit, we see another tiny eclipse. Count the days between them, and you get the length of its year, about 37 Earth days. This means we know exactly how far it must sit from its star, because orbital period and distance are locked together by gravity. Now we combine that with what we know about the star's luminosity. TOI-700 is cooler and dimmer than the Sun, yet TOI-700d sits much closer in. Put those pieces together, and we can estimate how much energy the planet receives. It turns out to be similar to the sunlight Earth gets, placing TOI-700d squarely in the Goldilocks zone where liquid water could exist on the surface. In the hunt for alien life, that single number, incident starlight, is absolutely crucial. It should be noted that size and orbit do not give us mass directly. For that, astronomers turn to 2 more subtle tools. One is radial velocity. As the planet orbits, its gravity tugs the star, making the star wobble slightly toward and away from us. That wobble imprints a tiny shift in the star's spectrum. Detecting it for such small planets is extremely challenging. So for TOI-700d, we also rely on statistical mass-radius relations, built from many other worlds where both properties are known. Optimistically speaking, those relations strongly suggest TOI-700d is rocky, not a puffy mini Neptune. But here is the pattern interrupt. Even with all this beautiful data, there is still so much we cannot see. Transits do not show us continents, oceans, or clouds. They do not reveal whether the atmosphere is thick with nitrogen and water vapor, thin like Mars, or stripped away entirely. So it's time to find out the truth. These shadows are not the end of the story. They are the starting conditions. With size, orbit, and estimated stellar energy in hand, climate modelers can already run detailed simulations of TOI-700d's winds, temperatures, and possible seas. And in the next section, we will step inside those simulated alien weatherscapes. So, could anything actually live there? But with all that in mind, we have to pause and ask a very simple question with a very non-simple answer. So, could anything actually live there? On paper, TOI-700d looks almost suspiciously promising. It is an Earth-like planet in terms of size, only a little larger than our own world. It orbits in the Goldilocks zone of its red dwarf star, receiving roughly the same stellar energy that Earth gets from the Sun. And this particular star, unlike many of its volatile cousins, appears relatively calm, with far fewer violent flares than TRAPPIST-1. In the hunt for alien life, that is a very strong starting checklist. This means that if you were designing a nearby target for habitability studies, TOI-700d would land near the top. Short year of about 37 days, stable orbit, no obvious signs of being roasted or frozen. Optimistically speaking, it feels like the kind of planet where oceans, clouds, and maybe even complex climates could exist. But while the headline numbers look friendly, the fine print is where things get difficult. The same close orbit that keeps TOI-700d warm also almost guarantees tidal locking. One hemisphere likely stares at the star in endless day, while the other sits in permanent night. What does a habitable world even mean when half of it never sees a sunrise? It should be noted that we also have no direct measurement of its atmosphere yet. Is there a thick protective blanket of air, or almost nothing at all? A dense, Earth-like mix could spread heat and allow liquid water. A Venus-like cloak of CO2 could turn the dayside into a pressure cooker. A thin, Mars-like skin might leave most of the surface frozen and airless, with only marginal pockets where anything could endure. And then there is the planet's past. Even a relatively quiet red dwarf today may have been far more active in its youth. Did early flares and high-energy radiation strip away water and other volatiles before life ever had a chance? Or did TOI-700d manage to hang on to its inventory, perhaps thanks to a strong magnetic field or repeated outgassing from its interior? So when astronomers carefully describe TOI-700d as potentially habitable, what are they really saying? Are we talking about lush forests, blue oceans, and a second Earth? Or just a world that might not be instantly lethal to hardy microbes clinging to a twilight band along the day-night boundary? So it's time to find out the truth about that word, habitable. The Goldilocks zone is necessary, but it is not sufficient. Many planets in this zone will still be barren, frozen, or scorched. To move beyond wishful thinking, we have to embrace the uncertainty and dive into detailed climate and atmosphere scenarios. In the next section, we will explore how different skies, oceans, and winds could make or break TOI-700d's chances for life. What we don't know yet. Uncertainties around TOI-700d. So if the Goldilocks zone is not a guarantee, how much do we actually know about TOI-700d? And how much are we just filling in with educated guesses? In the hunt for alien life, this is where things get uncomfortable, but also very interesting. Right now, we do not have a direct detection of TOI-700d's atmosphere. No spectrum, no clear chemical fingerprints, no cloud maps. This means every climate scenario we draw for this planet, lush ocean world, frozen desert, Venus-like hothouse, is built on plausible assumptions, not hard measurements. We know the planet's size and how much energy it receives from its red dwarf star, but the rest is still a blank canvas. It should be noted that some of the most important ingredients for climate are exactly the ones we cannot yet see. How thick is the atmosphere, if there is one at all? Is it dominated by nitrogen, like Earth, smothered in CO2, like Venus, or rich in water vapor from a global ocean? Are there reflective clouds on the day side, or a clear, dark sky that soaks up starlight? Even the surface matters. A world with scattered continents and shallow seas behaves very differently from a deep, planet-wide ocean with no land at all. And beneath that surface, the uncertainties continue. We only have an estimate of TOI-700D's mass, not a precise value, so its density and gravity are still fuzzy. This matters. Slightly higher gravity could help the planet hold on to a thick atmosphere for billions of years. Slightly lower gravity could let the star slowly strip that air away. Mountain ranges, ocean basins, and even how tall waves can grow all depend on these basic physical properties. Then there is the star itself. TOI-700 is a relatively quiet red dwarf today, which is great news for habitability. But stars evolve. In its youth, TOI-700 may have flared more violently, blasting the planet with high-energy radiation. That early phase could have boiled away oceans, split water into hydrogen and oxygen, and permanently reshaped the atmosphere's chemistry. We can only model these possibilities statistically, running thousands of digital histories to see which ones leave a habitable, Earth-like climate, and which end in a dry, airless rock. So, is this a dead end? Not at all. Climate scientists now routinely explore entire libraries of possible TOI-700D worlds, sweeping through different atmospheric pressures, gas mixtures, cloud patterns, and surface layouts. Optimistically speaking, some of those combinations produce stable temperatures, liquid water, and long-term habitability. Others plunge the planet into runaway greenhouse or global glaciation. So it's time to find out the truth. In the next section, we will step inside those simulations and ask what it would actually feel like to stand under TOI-700D's alien sky. Zooming out, how habitable is the TOI-700 system overall? We have talked about models and climates in isolation, but how does TOI-700 second look when we zoom out and see the entire planetary system around it? If we want to judge how habitable a world might really be, we have to look at its neighbors. The TOI-700 system orbits a cool red dwarf about 100 light-years away in Dorado. This star is smaller and dimmer than the Sun, but relatively quiet for its type, with fewer violent flares than many red dwarfs. In the hunt for alien life, that calm behavior matters because it gives any fragile atmosphere a better chance to survive for billions of years. So, let's begin by lining up its known planets. Closest in is TOI-700b. It is a small, likely rocky planet hugging the star in a tight orbit of just a few days. Surface temperatures there would be far above anything we would call comfortable, and any Earth-like atmosphere would struggle not to boil away. Next out is TOI-700c, also roughly Earth-sized, but still inside the inner, hotter region of the system. These inner worlds sketch the dangerous side of living too close to a red dwarf. Then we reach the Goldilocks zone. TOI-700D orbits at about 37 days, and TOI-700E, discovered later, circles even farther out with a period of around 28 days between C and D's path in projection, but receiving somewhat less energy overall. It should be noted that both D and E are close to Earth in size and mass, and they sit near or within the habitable band where liquid water could exist on a rocky surface. This means TOI-700 is not just a one-off curiosity, it is a multi-candidate habitable system. Here is the surprising part. All four of these planets orbit closer to their star than Mercury does to the Sun. The entire habitable zone is squeezed inward, wrapped tightly around the red dwarf like a narrow ring. But while that might sound claustrophobic, it also makes the system incredibly compact and efficient to study. Future telescopes can watch multiple potentially habitable planets transit the same star, using the same instruments under almost the same conditions. Optimistically speaking, having several Earth-like planets in or near the Goldilocks zone of a relatively quiet red dwarf makes TOI-700 one of the best nearby laboratories for testing our ideas about life. System-level dynamics, such as the gentle gravitational pulls between B, C, D, and E, can subtly stretch or tilt their orbits, changing long-term climate. Yet current orbital models suggest TOI-700d is probably stable enough to keep a roughly circular path for billions of years. So it's time to find out the truth. Among all these worlds, TOI-700d stands out as the most promising. In the next section, we will narrow our focus completely and step down, at least in our simulations, onto its surface to see what that strange, compressed, habitable zone really feels like from the ground. Orbiting in 37 days, the strange year of TOI-700d. If TOI-700d is the most promising world in this system, what does its calendar actually look like from the surface? Because before we imagine oceans, clouds, or even alien forests, we have to understand how this planet moves around its star. TOI-700d orbits its quiet red dwarf once every 37 Earth days. That is its entire year. So instead of 4 long seasons spread over 365 days, you would have a new year roughly every 5 weeks. It should be noted that around such a cool, dim star, seasons, if they exist at all, would not be driven by the same gentle tilt and orbit dance we know from Earth. They would be compressed, muted, or warped by something far stranger. What is that stranger effect? Tidal locking. Gravitational interactions between the planet and its star act like a cosmic brake, gradually synchronizing rotation and orbit. This means the same hemisphere of TOI-700d almost certainly always faces the star, just as the same side of our moon always faces Earth. One side lives in endless day, the other in eternal night. There is no sunrise, no sunset, just a star frozen in the sky over one point on the surface. Physically, though, TOI-700d is remarkably Earth-like. Its radius is about 1.1 times that of Earth, and the best mass estimates suggest a rocky world not far from Earth's mass. Surface gravity would probably be within a few tens of % of what we feel right now. So if you stepped out of a lander, your weight would feel broadly familiar. You would not float, you would not be crushed. The alien part is not how hard the ground pulls you down, but how alien the sky and the lighting would be. Because even though TOI-700d receives roughly the same total stellar energy as Earth, it gets that energy from a smaller, redder star. The spectrum is shifted toward red and infrared light. Colors would look different. Shadows might feel softer and deeper at the same time. In the hunt for alien life, that shift matters. Photosynthesis on this planet might favor darker, almost black pigments, tuned to drink in red light, rather than the bright greens we associate with plants on Earth. So let's begin to think about the real climate question. With one hemisphere baked in perpetual daylight and the other locked in freezing darkness, how is heat moved around? Do thick winds and oceans smear warmth from day to night? Or does the dark side collapse into an airless, frozen desert? Optimistically speaking, climate models suggest a third option, a habitable twilight ring along the terminator, that thin band where the star forever hugs the horizon. In the next section, we will step into that ring and ask what daily life means on a world that has no true day or night, only permanent alien light. If TOI-700d were Earth 2.0, the temperate atmosphere scenario. So if TOI-700d does not freeze its air on the dark side, or boil it off on the bright side, what is the most optimistic picture we can draw? In the hunt for alien life, climate scientists often start with a very simple, very familiar assumption: an Earth-like blanket of air. This means we give TOI-700d a roughly Earth-thickness atmosphere, dominated by nitrogen, with a dash of carbon dioxide and water vapor. It should be noted that this is not wishful thinking, but a standard baseline in many habitable zone exoplanet models. Nitrogen is chemically quiet. CO2 and water vapor provide a controllable greenhouse effect, and together they let us test how a planet in the Goldilocks zone of a red dwarf might actually feel at the surface. Now add oceans. Once you do that, the entire climate of this tidally locked world changes character. Instead of a dead, baked hemisphere and a frozen far side, the atmosphere and seas can act like a giant heat engine. Warm air under the eternal day side rises, flows toward the night, cools, and sinks. Surface winds drag ocean water with them. Powerful currents carry heat from the substellar point outward and then back again along deeper return flows. So let's begin to imagine the result. No side of the planet is allowed to drift to extreme, lethal temperatures for long. Right under the point where the star hangs overhead, models predict something dramatic. A vast, warm, cloudy region with towering storm clouds driven by intense convection. Picture a slow-motion hurricane that never quite moves, a permanent storm system venting heat to space. Around it, belts of thick cloud reflect some of the red dwarf's light, preventing the surface from turning into a global desert. As you walk away from that blazing zenith toward the terminator, the climate would gradually relax. Winds would still be strong, but temperatures would fall from tropical toward pleasantly mild. Near the day-night boundary, the star would hover forever near the horizon, casting copper-red light through layered clouds. In many climate simulations, this ring-like zone becomes the most habitable, cool enough to avoid runaway greenhouse, warm enough to keep water liquid. In this Earth 2.0 atmosphere scenario, large regions of TOI-700d could host open oceans, lakes, and perhaps even archipelagos of rocky islands. Surface temperatures in the twilight belt might resemble Earth's temperate zones, with long-term averages between a few degrees below freezing and the low 20s Celsius. Optimistically speaking, that is more than enough room for complex chemistry and maybe biology to take hold. So it's time to find out the truth. Is this just a beautiful theory or something the real data can support? Climate models tailored to TOI-700d suggest that such an atmosphere-ocean configuration is physically plausible for this system. And if that is correct, then we may be looking at one of the closest things in the nearby universe to an Earth-like world, just lit in a way no human has ever seen. But what would it actually feel like to stand in that eternal sunset? And how would daily life unfold on a planet with no true day or night? The Terminator cities, life along the eternal twilight line. To answer that, we have to follow the light. On a tidally locked planet like TOI-700d, the most important place is not the blazing substellar point or the frozen midnight hemisphere. It is the thin, planetary-scale borderland in between, the terminator. This is the narrow ring where day meets night, where the red dwarf star forever hovers on the horizon and never quite rises or sets. Here, the light arrives at a low angle, filtered through the atmosphere in a permanent deep orange glow. The energy from the star is weaker than at the dayside center, but far more gentle and stable. This means temperatures could hover in a relatively mild range, especially in an Earth-like atmosphere scenario, where winds and clouds help spread heat around the planet. In the hunt for alien life, that kind of long-term stability is priceless. So what would water do in this strange climate engine? On the day side, closer to the substellar point, oceans might simmer under thick clouds, driving powerful storms. On the night side, water vapor would freeze out as ice caps and glaciers. But along the twilight ring, rivers fed by melting ice could flow back toward the light, pooling into lakes, and even narrow, elongated oceans that trace the terminator itself. These seas would rarely fully freeze, yet never boil away because the stellar input hardly changes. It should be noted that climate models of tidally locked worlds already hint at this behavior, a natural refuge emerging between extremes. If TOI-700d has enough air and water, the Terminator could be its true Goldilocks zone, a continuous coastline of habitability wrapped all the way around the planet. Now imagine that ring lit up by cities. Architecture would be optimized for a star that just hangs there, eternally on the horizon. Instead of east-facing windows for sunrise and west-facing for sunset, every building would be oriented toward that single glowing direction, like a planet-wide sundial frozen in mid-afternoon. Streets would run in arcs and spokes, maximizing exposure to the dim, reddish light. Public squares might be permanently bathed in copper-colored dusk with high, reflective surfaces to bounce every photon deeper into the urban canyons. Solar arrays would tilt toward the horizon, forming glittering terraces outside the bright core, while on the night side edge, insulated habitats would cling to the last usable warmth. Life itself would likely organize into concentric ecological bands. Heat-loving organisms, perhaps dense forests or alien reefs, would push toward the dayside, tapping higher energy but enduring harsher storms and stronger radiation. Cold-adapted species would creep out into the darkness, feeding on winds that carry moisture and organic material from the lit hemisphere. Between them, right in the temperate belt, a rich biosphere could flourish, migratory creatures tracking the best conditions along the ring, airborne plankton drifting in slow, global circuits, and, optimistically speaking, civilizations trading along a continuous twilight coastline. But how would it feel, psychologically, to live under a sky that never changes, where time is no longer marked by sunrise or sunset? So let's begin to explore what that might do to culture and consciousness, after we first examine what happens when TOI-700d's climate is much less forgiving. When habitable zones go wrong, the Venus-like greenhouse option. But what if that less forgiving climate is not just challenging, but catastrophic? In the hunt for alien life, we often celebrate planets in the Goldilocks zone as potential second Earths. Yet there is a darker possibility hiding inside that same orbital sweet spot. A world that looks perfect on paper, but in reality is much closer to Venus. TOI-700d could be one of those worlds. So it's time to find out the truth about the Venus option. Imagine TOI-700d wrapped in an atmosphere tens to even hundreds of times thicker than Earth's, made mostly of carbon dioxide. Sunlight from its quiet red dwarf star pours in, the surface warms, and that dense blanket traps the heat with brutal efficiency. This means temperatures do not just creep above freezing or even tropical levels. They can rocket far beyond the boiling point of water until rock itself begins to soften, and any ocean that once existed has long since vanished into steam. How does a planet in a habitable zone end up like this? It should be noted that the key may lie in its early history. If TOI-700d started with abundant surface water, strong greenhouse heating on the tidally locked dayside could have turned those oceans into a thick, global steam atmosphere. High-energy ultraviolet light from the young star would then split those water molecules apart, a process called photodissociation. Hydrogen, being light, escapes to space. Oxygen is left behind to react with surface rocks, iron, and volcanic gases. What remains in the long run is carbon dioxide, piling up relentlessly. At some point, the planet crosses a tipping point, a runaway greenhouse. More heat means more water vapor, which traps more heat, which releases even more gases from the crust. The feedback loop locks in, and the world races away from anything we would call habitable. On the surface of such a TOI-700d, the dayside would be a broiling inferno, under pressures that could crush a submarine. Winds in the upper atmosphere might super-rotate, whipping around the planet in just a few days, dragging heat from the star-facing side to the night side. Instead of friendly water clouds, you could have thick decks of sulfuric acid or other exotic droplets, reflecting visible light but trapping infrared, turning the whole system into a pressure cooker. Even the eternal night would not offer relief. Efficient heat transport would keep the dark hemisphere stiflingly hot. Now, TOI-700 itself is relatively calm for a red dwarf. It flares less than many of its cousins, which, optimistically speaking, reduces the odds of the most extreme atmospheric erosion and wild climate swings. But while that makes the Venus outcome less likely than around a hyperactive star like TRAPPIST-1, it does not rule it out. Initial water content, volcanic activity, and even the timing of tidal locking could all push TOI-700d toward paradise or toward hothouse. And here is where the observational stakes become enormous. From far away, an Earth-like and a Venus-like TOI-700d could have almost identical sizes, masses, and orbits. Only by dissecting its atmosphere, measuring carbon dioxide, searching for water vapor, probing cloud heights, can future telescopes tell us which face this planet is truly showing us. So let's begin to ask a more unsettling question. If we do discover that TOI-700d is a blazing hothouse, what would that imply about the fate of other Earth-like worlds we have been quietly counting on? Ocean world, desert world, or bare rock? Other faces of TOI-700d. If TOI-700d is not a runaway hothouse, what else could it be? In the hunt for alien life, this is where things become strangely beautiful, because the same planet at the same distance from its star can wear very different faces. One possibility is that TOI-700d is an ocean world. Not some oceans, but a true global sea with no continents at all. Imagine standing on a small island of rock, if any exist, under a fixed red dwarf star, while endless water stretches to every horizon. With deep oceans and a reasonably thick atmosphere, heat from the day side could be transported efficiently to the night side by winds and currents. This means the temperature contrast between eternal day and endless night might be surprisingly small, wrapped in a blanket of clouds that reflect some starlight and trap some heat. In such a world, storms would circle the substellar point, where the star hangs motionless in the sky. Jet streams could sweep warmth across the terminator into the dark hemisphere, where the ocean might freeze only at great distances from the light. Could life thrive in a global ocean like this, feeding on chemical energy upwelling from the depths? Optimistically speaking, this might be one of the most habitable versions of TOI-700d we can imagine. But while an ocean world is inviting, a very different picture is also possible: a desert planet. Here, most of the water is locked away in small polar seas, high-altitude clouds, or underground aquifers, leaving vast rocky plains and dune fields under a thin, dry sky. With less water vapor to move heat around, the day side could swing from scorching surface temperatures to freezing nights just a short distance into the dark hemisphere. The atmosphere would still soften those extremes, but not nearly as well as deep oceans. Pattern interrupt. What if there is almost no atmosphere at all? If early flares from the red dwarf stripped TOI-700d's air, we might be looking at a near airless rock. On the day side, bare regolith could bake under unfiltered starlight. On the night side, temperatures could plunge to cryogenic levels. Only underground, where rock insulates and perhaps traps ancient ice, would there be any realistic refuge for life. It should be noted that worlds like Mercury in our own system show us how brutal such airless temperature contrasts can be. Across all these scenarios, the key player is the atmosphere, its pressure, composition, and clouds. Thick, water-rich air boosts cloud cover and albedo, reflecting light and moderating climate. Carbon dioxide raises surface temperatures through the greenhouse effect. A thin atmosphere does little of either. So it's time to find out the truth. Which combination allows stable liquid water over billions of years? Until we have direct atmospheric data from future telescopes, we must keep ocean world, desert world, and bare rock all on the table. Climate models, however, already hint that only some of these phases of TOI-700d can sustain long-term liquid water, and those are the ones we will focus on next. Winds that never stop, weather on a tidally locked planet. If TOI-700d can hold on to an atmosphere, what would the weather actually feel like on a world with no sunrise or sunset? In the hunt for alien life, it's not enough to know where liquid water could exist. We also have to ask whether the winds and storms would let anything survive there. On a tidally locked planet, one point on the surface always faces the star. That substellar point would be a permanent bullseye for energy from the red dwarf, a hotspot that never moves. Air there would be heated over and over, rising in a towering column. It should be noted that many climate models predict this region would host a giant, long-lived storm system, a bit like Jupiter's Great Red Spot, but pinned directly under the star and fed constantly by stellar radiation. So what happens to all that rising air? Once it reaches high altitudes, it has to go somewhere. It would spread outward, flowing toward the night side in vast, planet-spanning rivers of wind. As it travels into darkness, it cools, becomes denser, and eventually sinks on the cold hemisphere. Then, hugging the surface, it rushes back toward the day side to replace the air that just rose. This means TOI-700d would likely be wrapped in enormous circulation cells, stretching from the substellar point across the twilight band all the way to the night side. But while the pattern is simple, the details depend critically on how thick the atmosphere is. With a dense, Earth-like, or even thicker atmosphere, temperature differences between day and night get smoothed out. The result? Broad, powerful jet streams that blow steadily for thousands of kilometers, especially around the Terminator region. You might stand in the Goldilocks zone, ring of twilight, and feel an almost constant, strong wind, more like living on the deck of a ship that never enters harbor. If the atmosphere is thin, the story changes. Dayside rock could bake, while the nightside freezes hard. Local contrasts sharpen, and instead of smooth jets, we would see violent gusts, turbulence, and sharp weather fronts where hot and cold air collide. Optimistically speaking, a moderately thick atmosphere would be the most habitable compromise. Enough to move heat, but not so wild that the surface is scoured by endless storms. Now add water. If TOI-700d has oceans, or even scattered seas, moisture evaporated near the substellar storm could be lofted high and then carried into permanent night. There, under a black sky, it would condense into thick clouds, mist, or even fall as snow, building bright ice deposits on the dark hemisphere. In effect, the planet could run an exotic, one-way water cycle. Liquid and vapor on the day side, snow and ice on the night. These global winds are not just a curiosity. They decide whether the twilight ring stays relatively calm and stable, or whether it is hammered by constant storms and brutal temperature swings. So it's time to find out the truth. Are we looking at a gentle, habitable breeze, or a world where life must cling on in the eye of an endless hurricane? Living under a fixed star, light, color, and photosynthesis. If those winds decide where storms can rage, the star decides something even more fundamental, what it feels like to be alive there. TOI-700 is a cool red dwarf, and that changes everything. Instead of our sun's white-yellow glare, this star pours out deep red and infrared light. This means that even if TOI-700d is perfectly habitable in the classical Goldilocks zone sense, the very color of reality on this planet would be shifted. the sky, the oceans, even the way eyes and leaves evolved to catch photons would all respond to a different spectrum. On Earth, plants use chlorophyll that is tuned to visible light, reflecting green and absorbing reds and blues. Under TOI-700's glow, that strategy wastes precious energy. So let's begin to imagine photosynthetic life that is optimized for a redder universe. Pigments could be tuned to soak up deep red and near infrared, grabbing every long wavelength photon they can. To our eyes, transported there in spacesuits, the dominant vegetation might look very dark, even purple or almost black, because it reflects almost nothing back. It should be noted that we already see hints of this strategy in our own system. Some Earth microbes use so-called bacteriochlorophylls to harvest near-infrared light in dim environments. On TOI-700d, that niche behavior could become the main rule. Forests of low, dense, black-leaved organisms hugging the Terminator could be the most efficient solar panels that biology can build. But what is it like to stand under a star that never moves? Because TOI-700d is almost certainly tidally locked, the star would hang fixed in the sky over the day side. No sunrise, no sunset, just a permanent copper-red disk frozen above one point on the planet. Shadows would always point in the same direction, etched into the landscape like geometry that never relaxes. The brightness and color of the sky would barely change from hour to hour, unless clouds drifted past or the atmosphere scattered the red light into a perpetual dim glow over the twilight band. On Earth, nearly all complex life uses circadian rhythms tied to the day-night cycle. But while light is our master clock, it would be unreliable here. In the hunt for alien life, TOI-700d forces us to consider other timekeepers. Organisms might lock their internal cycles to tiny temperature swings as winds shift, to regular patterns in weather, or to biochemical clocks that free run with only occasional synchronization cues. Human settlers might need engineered lighting schedules inside habitats just to stay mentally stable. Optimistically speaking, TOI-700d could tick every box for being physically habitable, yet still feel profoundly alien to our senses and biology. A red sky, black forests, a star that never moves, and bodies that no longer trust sunrise to tell them when to sleep. And if that is the case, then the real question becomes, could we truly adapt to such a world? Or would TOI-700d demand a different kind of human altogether? A day in the life on TOI-700d, human habitats on the Twilight Ring. So what would that different kind of human actually live like on TOI-700d? Imagine opening your eyes in a home built along the Twilight Ring, where the red dwarf star never rises and never sets. It just hangs, forever near the horizon, pouring a perpetual golden red glow through narrow, slit windows. Those windows are not for the view. They are precision instruments, shaped and shaded to let in just enough light and not too much heat. You step into a corridor that curves gently, and only then do you remember the entire city is an arc. Instead of a grid like on Earth, our settlement follows a line of constant illumination, tracing the planet's terminator. On one side of town, the landscape fades toward the dark hemisphere. On the other, the terrain brightens toward the blazing day side. This means every street, every greenhouse, every power station is mapped to a specific band of temperature and light. Transportation here is not just north-south, east-west. It is toward day and toward night. Trains and cargo lines run along the Twilight Band, linking arc cities that encircle the planet, while high-speed maglev lines cut across, diving into cooler zones for refrigeration and industry, and reaching into warmer regions where solar collectors drink in the star's energy. In the hunt for alien life, we often imagine wild ecosystems. But first we have to imagine this very human infrastructure. The engineering challenges are relentless. The day side is a constant power source with huge solar farms always facing the star. But the night side is an endless sink of cold. So we shuttle heat and electricity across the terminator, store energy in vast batteries and thermal reservoirs, and use the atmosphere itself as a conveyor belt. It should be noted that if TOI-700D has strong winds flowing from hot day to cold night, our buildings must be aerodynamic shells, anchored deep, shaped to bend the wind rather than fight it. Can you picture skyscrapers that look more like dunes than towers? Inside, our relationship with time breaks. There is no sunrise to mark morning, no sunset to close the day. So let's begin to imagine artificial cycles, lights brightening and dimming on a strict schedule, work shifts tied to clocks, not to the sky. Children might learn that a day is 37 Earth days long in orbit, yet their own rhythm is a carefully curated 24 hours. Here comes the pattern interrupt. Festivals without dawn. Instead of watching a sun appear, communities might celebrate orbital milestones, periastron feasts, when the planet is closest to the star, or Terminator parades, marching along the line of eternal twilight. Art and religion could center on the unblinking star, a symbol not of change, but of constancy. What kind of myths grow on a planet where the heavens never move? Optimistically speaking, all of this assumes TOI-700D really has a stable, Earth-like atmosphere and a gentle climate in its Goldilocks zone. If the air is thinner, hotter, or more violent than we hope, human life may be forced into sealed habitats, buried arcologies, or even orbital stations watching the twilight ring from above. So it's time to find out the truth. What does the real TOI-700D actually look like when we point our best telescopes at it? Could complex life evolve here, or just microbes? If we could actually see TOI-700D's surface, what kind of life would we expect to find there? Are we looking at a world of oceans full of microbes, or a place where forests and animals could, in principle, evolve under an alien red sun? To answer that, we need to separate two very different questions. One is basic habitability. Does this planet have liquid water, a stable range of temperatures, and an atmosphere thick enough to move heat around? That is the minimum ticket for chemistry to keep running. The other is far more demanding. Can complex, multicellular life arise and persist for hundreds of millions of years? This means long-term climate stability, steady energy from the star, and enough environmental diversity to drive evolution. On Earth, complex life took over 3 billion years to appear. It should be noted that during that time, our planet's continents drifted, ice ages came and went, and the sun slowly brightened. Those changes repeatedly reshaped habitats, opening new evolutionary pathways. So what happens when we move that story to a tidally locked world in the Goldilocks zone of a red dwarf? Tidal locking is both a blessing and a curse. The permanent day side of TOI-700D could host a bright, relatively stable climate under a fixed red star, while the night side is plunged into endless darkness. But while Earth spins to share daylight around the globe, here the truly comfortable band may be a narrow twilight ring around the terminator, limited habitable area, strong day-night temperature contrasts, and possibly violent storms trying to redistribute heat could all reduce the number of safe, diverse niches where complex ecosystems can experiment. In the hunt for alien life, that does not necessarily stop microbes. If TOI-700D really has an Earth-like atmosphere and oceans, microbial life is, at least, reasonably plausible. Single-celled organisms are astonishingly adaptable. On Earth, they thrive in boiling vents, polar ice, deep rocks, and places with extreme gradients between hot and cold, light and dark. A tidally locked planet naturally creates those gradients. This means the day side, night side, and terminator could each host their own microbial communities, feeding off chemical energy, starlight, or even slow geothermal heat. But what about large, mobile organisms? That is where things become highly speculative. Any animal-sized life form on TOI-700d would face a sky where the star never moves. Fixed light direction would shape everything from vision to plant-like structures. Would creatures migrate along the terminator, following the most comfortable temperatures? Would they specialize in either the bright, stormy day side or the cold, calm night side, perhaps glowing or using infrared senses to navigate? Optimistically speaking, if complex life can adapt to such extremes anywhere in the universe, a quiet red dwarf system like TOI-700 offers a decent stage. We cannot assign real probabilities yet, but TOI-700d is at least a strong candidate for basic habitability. And that alone makes it a prime target for future telescopes searching for biosignatures in its atmosphere, even if we never see alien forests silhouetted against that unmoving red star. So let's begin asking the next question. What, if anything, could our instruments actually detect from such distant hypothetical ecosystems? What would count as proof? Biosignatures on TOI-700d. So if TOI-700d might be habitable, how would we actually prove that something is alive there? In the hunt for alien life, this is where things get wonderfully complicated. When astronomers talk about biosignatures, they're not looking for a single magic gas that screams life. Instead, they look for combinations of gases and atmospheric features that are extremely hard to sustain in large amounts without biology constantly refreshing them. Oxygen sitting alongside methane in a stable atmosphere is the classic example. On Earth, those two should rapidly react away, yet they persist together because life is always producing both. For a world like TOI-700d, orbiting a relatively calm red dwarf in the Goldilocks zone, there is a short list of target gases that would immediately grab our attention. Oxygen itself and its ultraviolet-produced cousin, ozone, would hint at powerful chemistry and maybe photosynthesis. Methane, especially if it coexists with oxygen or ozone, would be another red flag for biology. Nitrous oxide is even more interesting because on Earth it is strongly tied to microbial activity. It should be noted that certain organic hazes, like the smoggy layers we see on Saturn's moon, Titan, could also signal complex chemistry that life might exploit. And wrapped around all of this is water vapor, the sign of an active hydrological cycle moving energy and nutrients across the planet. But how could we possibly detect these fragile fingerprints of life from 100 light years away? Telescopes like the James Webb Space Telescope and even more powerful future missions can watch as TOI-700d passes in front of its star. A tiny fraction of the starlight will filter through the planet's atmosphere during each transit. By spreading that light out into a spectrum, we can see which wavelengths are missing, carved away by specific molecules. This means every gas leaves a kind of barcode, and with enough observations, we can start to read it. However, context is everything. Red dwarfs can pump out high-energy radiation that breaks apart molecules, and tidally locked planets can have unusual temperature patterns and chemistry. Some gases that look biological at first glance can be created abiotically by volcanoes, photochemistry, or even by the star's light, splitting water and reshuffling the fragments. So it's time to find out the truth, very carefully. Before anyone claims life, scientists must exhaust all the non-biological explanations. Optimistically speaking, even a tentative, noisy hint of an oxygen-methane combination or unexpected nitrous oxide on TOI-700d would be revolutionary. It would force us to confront the possibility that life is common around small red stars, not a rare Earth-only accident. But if the atmosphere does whisper of life, what kind of world would that whisper be describing? And how alien would that biology feel up close? JWST and beyond, how we'll actually study TOI-700d's air. If the atmosphere is whispering, how do we actually listen from 100 light years away? To answer that, we have to talk about the telescopes that can turn those whispers into real data. The James Webb Space Telescope is our first serious tool for this job. In principle, JWST could watch TOI-700d every time it passes in front of its red dwarf star, and every time it slips behind it. During a transit, a tiny fraction of the starlight filters through the planet's atmosphere. Different molecules absorb different colors of light, so by measuring those colors, we can infer what the air is made of. During a secondary eclipse, when the planet disappears behind the star, the small drop in infrared light reveals how much heat the planet itself was emitting. This means, in the hunt for alien life, we are essentially looking for minuscule changes in the star's brightness, changes of just a few parts per million, spread across many wavelengths. From that, we can try to reconstruct the temperature structure of the atmosphere, whether there is a strong greenhouse effect, and even whether the day side is blazing hot while the night side is freezing. But while the method is elegant, the reality is brutal. TOI-700 is relatively faint, and TOI-700d is almost exactly Earth-sized. The signal we care about is buried deep in noise from the instrument, the star, and even our own data processing choices. It should be noted that extracting a spectrum for such a small, potentially Earth-like planet around a distant red dwarf will require many, many repeated transits. We could be talking about dozens of observations, carefully stacked, with every systematic effect modeled and removed. Pattern interrupt. What if we could just take a picture of TOI-700d instead? Not a fuzzy light curve, a direct image. That is where future missions come in. On the ground, extremely large telescopes like the ELT, the 30-meter telescope, and the Giant Magellan telescope aim to use advanced adaptive optics to separate the planet's faint light from its star. In space, concepts like LUVOIR or HABEX imagine giant mirrors with star shades or coronagraphs that can block the starlight and let the reflected light from the planet itself shine through. So let's begin to see TOI-700d not just as a transit target, but as a future pale dot we might directly image. If these efforts succeed, what would success actually look like? Broad atmospheric features, a strong CO2 band pointing to a dense greenhouse, or water vapor hinting at clouds and maybe oceans. Constraints on surface pressure and temperature that tell us whether the Goldilocks zone is truly habitable here, or just a mirage. In reflected light, subtle color differences could betray ice, rock, or even global oceans. Optimistically speaking, TOI-700d is exactly the kind of planet that will justify these billion-dollar instruments. It sits right on the edge between a second Earth and a second Venus, a potential home for life, or a warning. So it's time to find out the truth. If we found oceans and oxygen, would we call it a second Earth? So if those instruments delivered the dream spectrum, oceans, clouds, and oxygen, what then? Would we finally point at TOI-700d and say, without hesitation, there, that's our second Earth? Imagine the data first. JWST and its successors split the starlight as the planet passes in front, and the atmosphere quietly gives itself away. Water vapor bands, hints of reflective clouds, a strong signal from oxygen, maybe even paired with methane. In the hunt for alien life, that combination would be explosive. This means we would be looking at a world with active chemistry, probably long-lived oceans, and a sky that on paper sounds remarkably familiar. But while the ingredients might match, the recipe does not. TOI-700d almost certainly keeps one face locked towards its red dwarf star, its year only 37 days long. One hemisphere would endure eternal daylight under a dim, reddish sun. The other would sleep an endless night. Does a planet where the sun never rises or sets really qualify as Earth-like, no matter how much oxygen or water we detect? It should be noted that astronomers already use Earth-like in a surprisingly narrow way. We usually mean a rocky planet with roughly Earth's size and mass, receiving similar energy in the Goldilocks zone, with an atmosphere that is not dominated by hydrogen or by a Venus-style blanket of CO2. By those metrics, TOI-700d is already a strong candidate. Its radius is close to Earth's, its insolation is comparable, and climate models show that with a modest atmosphere, it could keep liquid water stable. However, rotation state and stellar type are now moving from footnotes to front page. A tidally locked world around a red dwarf experiences gravity, light, and weather in patterns no one on Earth has ever seen. Jet streams might circle the permanent day-night terminator. Oceans, if they exist, could pile heat toward the substellar point, while the far side freezes into a dark, icy reservoir. Habitable, yes. But is that still Earth-like, or something new? Optimistically speaking, TOI-700d might force us to expand our imagination. Perhaps it becomes the prototype of a new category, worlds that are habitable but not Earth-like, cousins rather than clones, places where life could take root under red skies with alien constellations frozen over a single point on the horizon. You can already hear the cultural debate, right? Headlines shouting, "Second Earth found just 100 light-years away," while cautious scientists insist on longer phrases like, "temperate, potentially habitable exoplanet." Which one would the public remember? The dramatic version, of course. The idea that there is another place, not impossibly far away, where oceans shimmer and oxygen fills the air is almost irresistible. So it's time to find out the truth. When we say another Earth, do we really mean a twin, nearly indistinguishable from home? Or are we willing to embrace a broader family portrait, where TOI-700d is not a mirror, but a strange, compelling cousin we are only just beginning to understand? Human bodies, human minds. Could we really adapt to TOI-700d? If TOI-700d is that strange cousin, the real question is, could we actually live with it? What would it do to our bodies, our minds, and our entire idea of daily life if we tried to call this planet home? On Earth, our biology is wired to a 24-hour rhythm. Light increases, hormones shift, we wake up. Darkness falls, other hormones rise, we sleep. But on a tidally locked world in the Goldilocks zone of a red dwarf, that natural clock is shattered. The star just hangs there, frozen in the sky over the substellar point. This means our circadian rhythms would have almost no external anchor. Colonists would likely need strict artificial lighting cycles, timed sunsets and sunrises indoors, and even pharmacological help to keep sleep, metabolism, and mood from drifting dangerously out of sync. It should be noted that the light itself would feel alien. A cooler red dwarf emits a redder, dimmer spectrum than the sun. Outside, colors would be skewed toward deep oranges and blood-red shadows, with blues and greens looking muted or strange. Our eyes can adapt, but what about our emotions? On Earth, bright blue midday skies and changing daylight strongly affect mood. On TOI-700d, a dim, unchanging sky might slowly flatten our sense of time, and with it, motivation. Psychologists already see this with people in polar winters. Now imagine a whole planet that feels like a permanent late afternoon. So how would we even talk about a day there? In the hunt for alien life, we often focus on chemistry and atmospheres, but human culture is also built around the spin of our world. Without sunrises or sunsets, we would have to impose time from the top down. A day might simply be 24 Earth hours by law, while the planet's 37-day orbit becomes an almost irrelevant technical detail. Work shifts, weekends, even the idea of morning coffee and evening walks would be ritual rather than response to the sky. Different settlements might experiment, some following Earth time, others syncing to the planet's orbit, creating entirely new calendars and festivals around the slow march of the red star across the terminator. Radiation adds another invisible pressure. TOI-700 is quieter than many red dwarfs, but interstellar space still rains cosmic rays, and even a mostly calm star can flare on long timescales. This means habitats would likely be buried under regolith, wrapped in water tanks, or shielded with dense materials, turning many human spaces into caves lit by LEDs. Life outside, under that red sun, would be precious, but carefully rationed and monitored. Optimistically speaking, TOI-700d becomes a test. How flexible is human life, really? Can a species shaped by blue skies and spinning days truly thrive on a world that is habitable on paper, yet psychologically extreme? Or would our first permanent settlers discover that the hardest part of an Earth-like exoplanet is not the physics at all, but something far more personal that we have not yet measured? Why TOI-700d matters, even if it's lifeless. So if TOI-700d turned out to be completely lifeless, would that mean the story is over? Or would that actually be where the real science begins? In the hunt for alien life, a silent, barren TOI-700d would not be a failure. It would be a crucial, hard-won data point. Here we have an Earth-sized planet in the Goldilocks zone of a relatively calm red dwarf star, only about 100 light-years away. If that combination still does not produce a truly habitable world, then something important is missing from our assumptions. This means nature is telling us very clearly that the recipe for life is more demanding than right size, right orbit, right star. It should be noted that this kind of negative result is exactly what sharpens our models. Suppose JWST and future telescopes see a thin, stripped atmosphere, or a runaway greenhouse, or a frozen, airless rock. Each outcome feeds directly into climate and evolution simulations. Did TOI-700d start with too little water? Did geological activity shut down, ending volcanic recycling of CO2? Did the early star briefly flare harder than we thought, baking the atmosphere away? By matching the observed atmosphere and temperature to different histories, we refine the entire toolkit we use on every other exoplanet. Pattern interrupt for a moment. Imagine we learn that TOI-700d is dead, while another world around a more active red dwarf, like Proxima Centauri b, somehow looks more promising. That would be shocking, right? But while our intuition says calmer star equals better chances, the universe might disagree. Comparing TOI-700d to TRAPPIST-1's tightly packed system, to Proxima, and to future discoveries will let us map out which combinations of star activity, planetary mass, water inventory, and magnetic fields actually lead to long-term habitability. In that sense, every no is as powerful as a yes. When we cross TOI-700d off the list of likely living worlds, we are not just being pessimistic. We are carving away wrong ideas, closing off dead-end scenarios, and guiding precious telescope time toward the planets that really matter. So it's time to find out the truth, even if the truth is a quiet, empty sky. Optimistically speaking, the story of TOI-700d is not a simple paradise or bust gamble. It is one chapter in a much larger effort to measure how common, truly habitable, Earth-like planets are in our galaxy. Whether we find oceans and clouds, or bare rock and thin air, this world will anchor one corner of the diagram, and in the next section, we will see how upcoming observations could finally pin down where, exactly, TOI-700d sits on that map. From a fixed star to a fragile home, what we've learned. So where does all of this leave TOI-700d. We started with a dot of light around a distant red dwarf, and we have ended up with a surprisingly fragile set of possible homes. It should be noted that, on paper, the basics look almost ideal. TOI-700 is a relatively quiet M-dwarf, about 100 light-years away, cooler and smaller than the Sun, but steady compared with many of its flaring cousins. TOI-700d is almost Earth-sized, orbits every 37 days, and sits in the star's Goldilocks zone, receiving a similar amount of energy to Earth. Climate models, fed with different atmospheres and oceans, all agree on one thing. Several very different, stable worlds are possible. What are those worlds? One family of simulations gives us an Earth-like, temperate planet with a thick, mixed atmosphere and perhaps oceans that transport heat. In that case, the twilight ring between day and night could be truly habitable, with liquid water, clouds, and slow, dramatic winds under a fixed red star. In another branch, extra greenhouse gases push TOI-700d toward a Venus-like hothouse, with a dense CO2 atmosphere and scorching temperatures that sterilize the surface. Other solutions are more subtle. If the planet started with vast water but lost most land, it could be an ocean world, its dark side capped in ice and its day side wrapped in storm bands. If it formed dry, we might get a desert world, with habitable oases only near the terminator. And if early radiation stripped almost all gas away, TOI-700d might be little more than a thin atmosphere rock, dramatic to look at but hostile to surface life. Each scenario reshapes what chemistry, biology, and even technology would need to do to survive. But while we like to draw a simple green band around a star and call it the habitable zone, TOI-700d forces a deeper lesson. Habitability is not a yes or no switch. This means we must think about stellar behavior, atmospheric chemistry, rotation, tidal locking, and the planet's whole history as one interconnected system. Two planets at the same distance from the same star can live utterly different lives. In the hunt for alien life, that complexity matters. Imagining ourselves under a fixed red sun, no sunrise, no sunset, just a permanent glow in one direction, pushes us to ask, how would our biology adapt to eternal day or endless night? What cultures would grow around a sky that never changes? Would time feel different when shadows never move? Thinking through those details is not just science fiction. It trains us to see what is at stake when we label a world potentially habitable. Ultimately, TOI-700d connects back to the biggest question of all. Is life common in the universe, or rare and fragile? Optimistically speaking, a quiet red dwarf with an Earth-sized planet in the Goldilocks zone sounds promising. But as we have seen, a promising orbit does not guarantee a living world. So it's time to find out the truth. In the next section, we will look at how upcoming telescopes could finally tell us which version of TOI-700d actually exists. Would you move to TOI-700d? Your turn to decide. So let's begin with a very personal question. If TOI-700d turned out to be truly habitable, would you actually move there? We have walked through the data, the climate models, and the strange geometry of a tidally locked planet. We have imagined oceans flowing toward the light, winds racing from the hot dayside to the frozen night. But now we leave the simulations behind and step into something messier, your own choice. Would you stand in that twilight ring under a star that never moves in the sky and call it home? Think about the trade-offs. On the day side, the star hangs forever above one point, like a cosmic spotlight. No sunrise, no sunset. This means stable light, stable temperatures, and, if the atmosphere is thick enough, perhaps a remarkably predictable climate. Crops could grow under constant illumination, solar power would be abundant, and the Goldilocks zone would not just be an orbital distance, but a narrow belt on the surface. But while the physics sounds attractive, how would our minds cope with a sky that never changes? Now imagine the night side, eternal darkness, lit only by stars and the faint glow of the Terminator far away. It should be noted that this hemisphere might be locked in ice, an alien Antarctica stretching for half a world. Would you choose that quiet, cold frontier, maybe in underground cities warmed by geothermal energy? Or would you stay close to the bright edge where day and night meet? The twilight ring, the Terminator, is the compromise. Optimistically speaking, this narrow band could be the most Earth-like region on the entire planet. Permanent evening light, moderate temperatures, and perhaps clouds glowing copper and violet as the red dwarf star hovers on the horizon. In the hunt for alien life, many scientists think this is where complex ecosystems would cluster. But would you want to live in a crowded strip of habitability, with everything your society needs compressed into a ring around the world? So, your turn. Tell us in the comments. Are you a dayside colonist, a nightside pioneer, or a citizen of the Terminator cities? What kind of society do you think would emerge in each region? Would the bright side become an energy-rich technological core, while the dark side shelters more isolated, self-reliant communities? Here's a thought experiment. On a world without sunrise or sunset, how would you design a calendar? Would a day be one full orbit, 37 Earth days long? Or would you invent completely new cycles based on weather patterns or biological rhythms? How would you plan festivals when the sky never changes color? Picture a city in the twilight ring, streets aligned to the unmoving star, buildings casting permanent shadows, art built around a horizon that never shifts. What would painters focus on when there is no golden hour, only eternal dusk? What would home mean when direction is defined not by north and south, but by toward the light and toward the dark? So it's time to find out the truth about your own instincts. Would you stay on Earth or join the first ships to this quiet red dwarf system and step onto TOI-700D? In the next section, we will see how upcoming telescopes might force us to answer that question much sooner than we expect. Help aim our telescopes. Stay for the next world. That question is not just hypothetical. Within our lifetimes, we may see the first real data on TOI-700D's atmosphere, and we will have to decide what that means for us. In the hunt for alien life, this quiet red dwarf system is no longer science fiction. It is a real star, about 100 light-years away, with a real, Earth-sized planet in its Goldilocks zone, tidally locked and waiting. As JWST and the next generation of telescopes begin to split its faint starlight into spectra, we will start to see hints of clouds, gases, and maybe even oceans. So it's time to find out the truth together, not just once, but step by step as each new observation comes in. If you want to follow that unfolding story, this is where you can help aim our telescopes. Subscribe to the channel, like this video, and share it with someone who would actually move to TOI-700D if they could. This means the next time JWST releases data on this planet's atmosphere, you will be here with us as we break it down, line by line, from carbon dioxide and water vapor to the more speculative signs of a truly habitable, Earth-like world. It should be noted that TOI-700D is only one chapter in a much larger cosmic neighborhood. We will be returning to TRAPPIST-1, asking again whether TRAPPIST-1e can really keep an atmosphere under its active star. We will revisit Proxima b in the glare of our closest red dwarf neighbor, and we will chase new TESS discoveries as they appear. Compact systems, ocean worlds, and strange planets that stretch what we think habitable can mean. Your engagement is not just a number on a screen. Think of it as a kind of vote. When you comment, when you tell us whether you prefer TOI-700D, TRAPPIST-1e, or Proxima b, you are helping decide which system we explore next and how deeply we dive into its science. Which atmosphere models should we simulate? Which climate scenarios should we compare? Optimistically speaking, this channel can become a map of the nearby universe, drawn according to what you most want to understand. If you want a structured next step, do not stop here. Watch our deep dive on how JWST actually reads exoplanet atmospheres, how a tiny dip in starlight can reveal clouds, chemistry, and temperature on worlds we will never visit. Or continue with our comparison between TOI-700d and TRAPPIST-1e, and see why two Earth-sized planets in the Goldilocks zone can still lead to utterly different outcomes for life. Somewhere, right now, TOI-700d is circling its star once every 37 days, its bright side fixed under a small, steady red sun, its dark side turned forever to the deep. Our telescopes have not yet seen its true face, but they will. Stay with us, and you will be here for the moment that faint signal finally tells us what kind of world it really is.